Good day, everyone. Today we're going to be looking at the second half of our content on electricity and talking about what it means for something to offer electrical resistance. So I want to start with kind of an analogy to electrical resistance with a picture of the worst traffic jam you could ever imagine. Now, this traffic jam happened outside of a city in China. And as you can see over here on the left side of this kind of pavilion here that they've got, there's, 25, 30 lanes of traffic that are going through this location right here. And then on the other side, after they're done going through this kind of checkpoint that they're going through, this thing chokes down to, looks like 1, 2, 3, 4, 5 lanes of traffic. So inside of this green circle, this 30 lanes of traffic chokes down to 5, and I want you to think about what that does to the average speed of the vehicles that are on the road. And hopefully the answer is obvious, is that this is going to slow down these vehicles significantly. And this is kind of a good analogy to electrical resistance. We know that with our electrical circuits, we are moving charges from one place to another, and our wires function kind of like roads. And so in this case, I've got all of these charges over here on the left that are trying to move through. And as they approach this point, which I've got circled in green, where the entire thing narrows down, the speed at which those charges are moving slows down significantly. And that's kind of the role of electrical resistance. So resistance, or electrical resistance, is the opposition to the flow of electrical current. So it's anything that is going to resist those charges moving from one place to another. So it's going to slow down this electrical current. It's worth noting that all devices have some level of resistance. Even wires have resistance. So there's no perfect kind of resistance-free material, but some things are specifically designed to have resistance, and we call those objects resistors. So a resistor is a device that has a really specific or particular resistance, something that we are able to control. And so by controlling the resistance in a circuit, we can control how quickly charge is flowing from one place to another, and we can control the current that is moving through that wire. And so there's two different symbols that you might see for resistance. The first one, this is kind of an English or Cambridge version of what they refer to as a resistor. So that's kind of the Cambridge version. This down here is the most common one in the United States. This is the American common symbol for resistance. So it could show up on either one of these on a test or an assessment. So you should be familiar with both of them. Now, we can calculate resistance or the effect of resistance using an equation called Ohm's law. And so this was developed by a scientist named Ohm. No real surprise there. Scientists love naming things after themselves. And so he comes up with this law that says the amount of voltage that we have that changes from one place to another is going to be equal to the current that flows through that wire multiplied by the resistance that the circuit is providing. So voltage is equal to current times resistance. And the base equation is over here. If you would rather use kind of the testing triangle version of it, I've got that over here as well. And it's worth noting that voltage is always measured in a unit called volts. We're familiar with that, so that's a V. Current is measured in amperes or amps, which will be abbreviated as the letter A. And then resistance, our new thing, is going to be have the symbol that looks kind of like a horseshoe. This is the Greek letter omega. And so Ohm's law uses omega to represent resistance. And so those are three things that you should be able to measure in a circuit. And again, just kind of giving that information to you in table form. Resistance, the variable in the equation is R, but it's measured in ohms. Current, the variable in the equation is I, but it's measured in amps. And voltage, the variable is V, and this one is makes much more sense, and it's measured in volts. So keeping things simple. So if I was to give you kind of a sample equation, calculate the resistance of a light bulb if it is the only thing causing resistance in a 0.5 amp circuit connected to a 9-volt battery. And so I know that I have voltage right here, and this is a current because it's being measured in amps. And so if voltage is equal to current times resistance, and I can plug things in, I know I have a 9-volt battery, and that's connected to a 0.5 amp circuit, and we need to determine the resistance of my light bulb. I'm going to divide both sides by 0.5, because that'll allow me to clear this out over here. And so I'll find that I have a total resistance of 18 ohms. And so that is how we can use Ohm's law to solve for the resistance in a circuit. Now, how much resistance we have in a circuit is determined by how those resistors are set up. So let me introduce you guys to the concept of series and parallel. So if I have a circuit that has more than one route for electricity to take to go from the positive side of the battery to the negative side of the battery, we consider those things to be in parallel. And so most of the circuits that we have dealt with so far have been series circuits, where I can have a single path that allows me to go from one side of the battery to the other. In this case, I have in a parallel circuit, there's multiple ways for me to kind of complete a lap around the circuit. And so this is going to lead to different amounts of resistance. And the analogy that I like to use is Walmart, because it's one that we're all kind of familiar with, because we've all walked into a Walmart and we've looked at the front of that store and realized that they have like 50 checkout areas for us to possibly go through, but only like 1 or 2 of them are ever manned at a time. So let's say that they just have one of them open, and so everybody has to go through the checkout first, and then as you're trying to leave the store, they have somebody who asks to see your receipt to make sure you didn't steal anything. Well, that's 2 different stops that I have to make. That's a lot of resistance. That's slowing me down as I try to leave the store. Now pretend instead that I have 2 different checkouts open and that there's nobody at the door. So I can choose to go to this one, or I can choose to go to this one, but there's no way for me to have to go through both. Well, that's going to cut down on the amount of time it takes for me to leave the store. It's going to cut down on my total amount of resistance to me leaving the store. So if I have a situation that is in parallel resistors have less total resistance. And so if I set up a circuit in parallel, it's going to have less resistance. It's going to be easier for my electricity to move through. And because some of my electricity will go through 1 and some of my electricity is going to go through 2 in this case, what that means is there's actually less total resistance than me having just 1 resistor. So I can actually drive my resistance even lower by adding more and more branches. If I want to make the total resistance in my circuit even less, I could open up a 3rd branch on this, and that would cause my resistance to go even lower. So the more parallel branches I have, the lower my resistance is. The other nice thing about this is, let's say that this resistor burns out. Okay, I lose this altogether. Number 2 is still functional. This is still a way for me to go all the way around my circuit, which means parallel circuits, not only do they have much lower resistance, they also are much more resistant to a single component burning out. So they can then kind of maintain that way. So let's look at kind of a practice problem. Which of the following circuits has the least resistance and which one has the greatest resistance if all of my resistors have the same value? So what I've got is that the one that has the most number of parallel branches, in this case right here, this is going to be my least resistance because it's got the most options for my electricity to go through. Again, think of it like Walmart. This one has the most number of checkouts open, which means all the people trying to leave the store at once, they get to pick which line they want to go into, and the entire process goes faster. Now, if I made all of those people have to go through the same checkout and you only have one option, this would represent the most resistance or the greatest resistance. Spell that correctly. There we go. And that one's because there's only one resistor there. There's only one place, and all of my voltage has to go through that one spot. Good. Now, like I said, wires do have resistance. I am going to kind of skip this section. You do not need to be able to calculate wire resistance, so don't worry about that, or that, or that. But we should talk about, there's a couple different resistors that you should be familiar with, and the first one is a thermistor. So this is a resistor that specifically is designed to change its resistance based on the temperature of the room that it's in. So let's say that you have a thermostat, and your thermostat is set to 72 degrees in your house, and anytime that the temperature goes above 72, your air conditioning unit kicks on. That's being controlled by a thermistor, and what happens is as soon as the temperature changes enough, the resistance to electricity on your AC unit will suddenly drop, and the AC unit suddenly starts getting power and it kicks on. So a thermistor is a resistor that is sensitive to temperature. So think therm, kind of like a thermometer. That's what we're working with. So that's a thermistor. The other one that you might see is what's called a light-dependent resistor. And this is a resistor that, kind of like it's described in the name, is dependent on how much light there is in the room. So if you've got a night light in the bathroom that only turns on when the lights go off, that's being run on a light-dependent resistor. When it's detecting light, the resistance is really, really high, and it's not letting the light bulb turn on. But as soon as you turn the lights off, that resistance suddenly drops, and electricity can flow through the light bulb, and it turns itself on. So this I would use in a circuit that you want to be sensitive to how bright a room is. And so that's a light-dependent resistor. And you might see a reference to either of those on a test question. So that's the basics of resistance, and that's what you'll really need to know for this class. You might see more advanced resistance calculations if you take a college level physics class, but for right now, that's all you'll need to know.